So welcome back to the online Spintronics seminar series. I'm Kirill Beloshenko from University of Nebraska. For this 24th seminar, it is my pleasure to introduce Professor Stefan Blügel, who will talk about skyrmions in thin films and multilayers. Professor Blügel is director of the Institute for Quantum Theory of Materials at Forschungszentrum Jülich. And professor of theoretical physics at the Technical University of Rhine-Westphalia in Aachen. He's also head of the Peter Grünberg Institute and the Institute for Advanced Simulation at the Forschungszentrum. Dr. Blügel is an author of about 500 scientific publications, and his work has spanned a variety of topics in the electronic theory of solids, many of which are within the scope of Spintronics. Stefan's talk today will be about skyrmions. So it looks like it's going to be a 101 class that he's going to teach. So please welcome Professor Blügel, and thank you for joining us today for the seminar.
Yeah, thank you. I would like to start my talk thanking the organizers for the invitation, and even more so for setting up this online Spintronics seminar. I think it is really puts really the world community together, and we have heard the talks from Japan, from the United States, from France, and this time from Germany. I really feel like a part of a world community, and I really enjoyed very much. I really enjoyed the talks very much. Maybe the spin orbit torque and the skyrmions are the biggest novelties in Spintronics over the past 10 years. The field of skyrmions is in principle very rich. One includes mathematicians and mathematical physicists on one side, condensed matter people, material scientists, device people. It involves people with a focus on characterization of static and dynamical and transport properties. And it is an inspiration of new transport phenomena, such as, for example, just name one, chiral Hall effect. Skyrmions have been observed in bulk crystals, in thin films, in multilayers, in thicker films, also at room temperature. The field is booming and blooming, and in 45 minutes, one cannot cover this all. That's not possible. Instead, I decided to say a few simple things about skyrmions, and then show some recent work on films and multilayers. So the main motivation is maybe to learn something about things which may be intuitively not clear or unclear, which I see sometimes in publications. What is a magnetic skyrmion? I think about a ferromagnetic state, like here in red. And on this ferromagnetic state, you have immersed some worlds, some magnetic worlds, which are finite in size. They are localized, and they can move on this ferromagnetic state like an ice hockey puck on an ice hockey field. And remember, an ice hockey puck is pretty hard, indifferent to a soap bubble. So these are kind of hard objects moving around, and can be moved around by, for example, a current. Usually they are three-dimensional spin textures localized in a two-dimensional space, but these spin textures is not arbitrary. So if you zoom into these worlds, you see, for example, that you have a winding magnetic texture, and if you look very carefully, you see that exactly each direction, each magnetization direction appears exactly once and covers the entire sphere of a surface, the surface of a sphere. So basically, we have a smooth mapping of the magnetic structure here, for example, by projection onto a sphere. And basically, the number of times you can cover the sphere by this magnetic structure is a topological number. We call it also topological charge. One can be actually calculated by knowing the magnetization field. So the skyrmion It's a smooth and extreme magnetization configuration. It is topologically non-trivial in opposite to the ferromagnetic state. Going from the topologically non-trivial to the trivial state, you require a non-smooth transformation. So every transformation which is smooth leaves you in your subspace of classification. If you want to move across, you have to go over a singularity. So we have skyrmions which have different handedness. So we have a counterclockwise skyrmions, for example, here. You see from the inside to the outside along the radius, the magnetization rotates counterclockwise, while here, for example, it rotates clockwise. Then we have nail-type skyrmions and we have block-type skyrmions. Both of them have the same topological charge. In my notation, it's -1. That means already you know by now that there is a smooth transformation which gives you somehow from this nail-type skyrmion to the block-type skyrmion. And the difference is basically the magnetization here in the nail-type skyrmion. The magnetization rotates in a plane of radius and z direction, whereas in the block-type skyrmion, it's in the direction tangential to the radius. Then we have skyrmions and antiskyrmions. What is the major difference of this? So this topological charge can be written as a product of a polarization. This is the magnetization at the origin, times a one-dimensional winding number. Sometimes in physics, we call this the vorticity. It's a one-dimensional winding number where you take basically the integral along a circle, and you basically calculate a one-dimensional integral. And you see here the integral is different. Here the vorticity is +1, but here the vorticity changes sign, and the vorticity is -1. Usually this skyrmion is called antiskyrmion. I think it is not a good notation because the word antiskyrmion comes from a time where the true skyrmion was a baryon. And of course, the opposite charge of this baryon was this antibaryon. But I think here in our field, it is better to call it multi-chiral skyrmion, because what you see is, if you look here you see, if you go from inside out, the rotation direction here would be counterclockwise, while here, along here, the rotation direction would be clockwise. So here you have basically a multi-chiral skyrmion, and this has some implication on the crystal lattice. But topology is not everything. We also have, so to say, the particle is defined by the field theory. Our field theory is the micromagnetic energy functional, which you see here as the first term is the exchange, the second term is the magnetic anisotropy, and the third term is the external magnetic field. And imagine we have now our skyrmions on this ferromagnetic state, and we immerse now a single skyrmion on this ferromagnetic state. When I'm asking now the following question: what happens to this total energy, to this micromagnetic energy, if I increase or shrink a little bit my skyrmion? And this I do by this stretching transformation. Basically, the magnetization goes over to a slightly different magnetization, which is the old magnetization, but scaled up in size. Then you see, due to this r² term here, you get here a lambda square term. And since you have here a first derivative square, you get here a 1 over lambda square term. And if you plot this function now as function of lambda, then you see the minimum of this function is at lambda equals 0. That means if you put your skyrmion onto this ferromagnetic state, described by this energy functional, the skyrmion will be squeezed to 0, will be squeezed to death, and your skyrmion might be a delta function or a singularity, or might not exist. And this is quite different from the one-dimensional state. If you have a one-dimensional particle, for example, then this r² here changes to r. This depends only on the stretching parameter lambda, but this is further depending on the stretching parameter 1 over lambda due to the first derivative square. On you see your energy as function of this lambda has a minimum, and this minimum you well know this is the domain wall, a typical domain wall. If you put a domain wall in your system, the domain wall may survive. So a crucial thing in this field of skyrmions is this Dzhalodzinsky-Moria interaction shown here. This Dzhalodzinsky-Moria interaction is basically a necessary condition for the skyrmions, and a necessary condition for the Dzhalodzinsky-Moria interaction is the existence of spin-orbit interaction and a broken inversion symmetry. And if you do now our stretching operation, you see that due to this additional term here, proportional, which has the one derivative here, our stretching scalability scales like 1 over lambda, and you finally have a minimum at finite lambda. So this Dzhalodzinsky-Moria interaction stabilizes your skyrmion. But from this analysis, we can actually learn quite a bit. So what you see is, if the Dzhalodzinsky-Moria interaction is small, if D, the strength of this Dzhalodzinsky-Moria interaction, if this is small, we expect the minimum at very small lambda. That means a small Dzhalodzinsky-Moria interaction gives you small skyrmions. This is sometimes confusing because sometimes people think large Dzhalodzinsky-Moria interactions give you small skyrmions. No, you see, if there is no Dzhalodzinsky-Moria interaction, the skyrmion collapses. So a small Dzhalodzinsky-Moria interaction gives you a small skyrmion. And you also see a very important quantity is obviously this magnetic anisotropy, because the magnetic anisotropy is the quantity which wants to squeeze the skyrmion to death. And therefore, there is this very fine balance between the Dzhalodzinsky-Moria interaction and the magnetic anisotropy. And this explains, for example, that the skyrmion phase diagram of a bulk sample and a sample which is grown by sputtering on a substrate can be quite different, because on a substrate, if you grow it on a substrate, you might introduce a small strain in your system. And this small strain changes the magnetic anisotropy, and this change of the magnetic anisotropy brings you in this skyrmion balance somewhere totally different. That is an important aspect. So basically, I told you also mathematicians think about these skyrmions, and I make it very short. Basically, what one can say about them is, suppose your magnetic anisotropy is not equal to 0, and you have a finite magnetic field, then the minimum of the energy, you can always find a skyrmion. If you have Dzhalodzinsky-Moria interaction, you always can find a skyrmion at appropriate B field. So whenever you know, there is somewhere a Dzhalodzinsky-Moria interaction around, then you also know there exists a B field which we finally lead to a skyrmion. So basically what they have proven is, if the parameter space is correct, among all non-trivial topologies, the skyrmion with the topological charge -1 is the one with the lowest energy. Since this skyrmion is a particle, behaves like a particle of finite size, has a certain stability, is of course very attractive as a new particle for spintronics, to make a disruptive change of information technology. And the unique properties of the magnetic skyrmions relate to high data density, to thermal stability, to high data flows due to fast motion, and to electrical detection, for example, due to non-collinear spin textures. So there's a strong motivation to make this particle fit for the field of spintronics So people study injection, the transport properties, the detection, the manipulation at reasonable fields and currents, make it suitable for room temperature electronics, and things like that. And this has a vast component of this is a kind of materials design, materials development, materials massaging. Let's have a closer look to this Jaluchinsky-Moriya interaction again, basically which we can describe as a Jaluchinsky-Moriya spiralization tensor and by a chirality tensor. And so you can write it down, and basically the crystal structure determines the structure of this chirality tensor. So basically your Jaluchinsky-Moriya interaction is given by a tensor quantity and basically a scalar quantity. And different geometries lead to different tensors. So you have one scalar degree of freedom, and this one scalar degree of freedom defines basically the size, and the sign defines the rotational sense. And then you have something which defines the symmetry type of the skyrmion due to the symmetry type of the lattice. And for example, the upper one here gives you the Bloch type skyrmion. On this one gives you the nail type skyrmion. On both of them are related by 90-degree rotation. And this one we call isotropic Jaluchinsky-Moriya interaction. It's a rank 3 bulk DMI tensor. And this one in 2 dimension is basically a rank 2 DMI tensor because the entry here is 0. And there are other crystals, for example, crystal with a D2D symmetry. They have, due to the symmetry, a different tensor elements. And this tensor element gives you, for example, an antiskyrmion. Well, this we discussed already as a Bloch skyrmion. So depending which crystal structure you are choosing, you get either a skyrmion or an antiskyrmion. And we have recently found out if the determinant of such a tensor is positive, then you have skyrmions. If it's negative, you have antiskyrmions. So basically we have the bulk systems, and a very famous one is the Bloch, the B20 systems, for example, manganese silicide, and they have the typical Bloch type skyrmions. Then we have the film systems, for example, palladium iron iridium. They have typically the nail type skyrmions. And then we have the D2 materials, which, for example, which exhibit antiskyrmions. And the question is, do we have also antiskyrmions in thin films? Not discovered yet. And if you look now at this spiralization tensor, we discussed the isotropic one, rank 3, the tetragonal and the cubic one, the T2D one. Then we have the film ones, which give you the nail type structure. But what we found out is that there is also a symmetry group, C2V, typically 110 surfaces, or lower symmetry, where something fundamentally changes. This Jaluchinsky-Moriya interaction is not anymore described by a single scalar quantity, but by two independent quantities. So it's not, we call that not the isotropic Jaluchinsky-Moriya interaction, but the anisotropic Jaluchinsky-Moriya interaction. So for some people of maybe who work in other fields, I would like to draw a relation. So if you construct a model which should give you the nail type skyrmion, a microscopic electronic model to represent the nail type skyrmion, then it would be a Rashba model. For the Bloch type skyrmion, it would be the Dresselhaus model. But here you have a symmetry which is a combination of Rashba and Dresselhaus. And since the Jaluchinsky-Moriya interaction has the same symmetry operation like the field-like torque, that means also in the field-like torque, you would have two independent parameters. And with these independent parameters, you can have now something which is different from the other skyrmions. You can have the antiskyrmion and the skyrmion simultaneously. And if your determinant is smaller than 0, the antiskyrmion is more stable, has a lower energy, and if it's positive, the skyrmion has a lower energy. And this is different from this antiskyrmion which we have seen in the D2D structure. In this D2D structure, you can only have one type of skyrmion, which is the antiskyrmion. My statement is not fully correct. Also there you can have two skyrmions, but one will be a chiral skyrmion and the other one will be a dipolar stabilized skyrmion. And in some circumstances, what you can have is that one of these quantities is 0. And then we call that a rank 1 DMI. And then in this case, the skyrmion and the antiskyrmion are energetically degenerate. So that means if you have such a material, you could have a skyrmion and an antiskyrmion at the same time in the material, and you could create a racetrack memory with two independent particles, which you can read out and have different resistances. This is a great advantage because you don't have to worry anymore about distances of particles. If you have only one particle, it's very important that you have the right distance. Otherwise, you cannot distinguish between a particle and 0 and 1. And at the same time, it offers you the possibility to logical devices. For example, when you have skyrmions and antiskyrmions, or skyrmions and antiskyrmions and skyrmions, you can build logic devices. So, of course, the motivation is kind of to find these materials which lead to sub 10 nanometer skyrmions at room temperature. This is certainly a bigger theme. And also, I think it is a theme. Additional would be nice to have skyrmions which run fast, which have high speed, which are stable, and so on. Now, I would like to dive a little bit deeper into the skyrmions. I would like to make a micromagnetic analysis of the skyrmion radius. So we know meanwhile our micromagnetic energy functional. And I make this reasonable ansatz that the skyrmion is actually symmetric, is a skyrmion tube. And therefore I write my magnetization as function of a profile, as function of the radius, and I assume nail type skyrmions. And these are basically the coordinates of the nail type skyrmions. And I have to find now the optimal profile, theta, and this I basically do by deriving the Euler-Lagrange equations, which gives me an equation for the profile, which you see here, that minimizes this energy functional. I admit this, you don't have to look too much about this equation. It looks very complicated. On the other hand, I simplified this already for you in the sense that, I work only with one-dimensionless parameter, which is this in micromagnetism well-known kappa parameter, which is a ratio between the exchange and anisotropy divided by the Jarodzinski-Moria square. And this equation I solved now by the shooting method for boundary conditions such that at the radius 0, the magnetization points down, and at infinity, it goes over to the ferromagnetic state. And in this equation enters also, basically the external B field is renormalized. And what is also interesting to know is that this parameter kappa can be also considered as a parameter of anisotropic rotation. So basically it is the ratio, this kappa is the ratio of the length of the homogeneous spin spiral versus the inhomogeneity, which is the ratio of the Jarodzinski-Moria interaction divided by the magnetic anisotropy. And the radius is given in units of the domain wall width. And the Skyrmion radius is defined as the magnetization, if the magnetization points in the plane, or if the Z component of the magnetization is 0. This is exactly at this angle pi half, and it means basically the radius is there where the magnetization points only in the plane. So roughly here. I'm solving now this equation for zero field to make it simpler and express everything in this domain wall width. This is the answer. This is a crazy function. I know the plot looks empty. It's totally crazy function, but what you see as function of kappa, the Skyrmion radius is extremely small. And what you see, if kappa becomes close to 1, the Skyrmion radius shoots up. So let's have a little bit a closer look of this function. So this function as function of kappa, you see it's nearly 0. From kappa 5 on, it rises, but then it rises very steeply. And here is kind of a logarithmic plot to see a little bit more how this function looks like. So it's a function which is rather nice, but suddenly it goes up. And more or less accidental, not fully accidental, but by luck, I would say, we found an analytic expression for the Skyrmion radius, which is related to this kappa, the logarithm of the kappa, and the root of the kappa. And this analytic function is good for kappa smaller than 2. And for kappa, for the radius larger than 1, it is this expression. I know you all know this W function. It is the Lambert W function, but I plotted it just for convenience. So this is 1 over W. This is W. The W is the inverse of this expression. And what this equation, these results have an important message for experimentalists. Because if you design your material stack such that you are in this regime where where things grow quickly, it means that if you have a sputtered sample, you have always fluctuations in your system on fluctuations on DMI, fluctuations of the magnetic anisotropy, maybe a little bit exchange. And that means you have small fluctuations in this value kappa. But it means you have huge breathing of the Skyrmion radius. And this huge breathing for the Skyrmion radius slows you down because now your hard disk, which moves, gains a kind of inertia because it always has to breathe up and down. And this slows the Skyrmion down. So optimally, it would be that you are in this regime. But imagine, for example, you want, so this curve is with respect to the domain wall width. So imagine you want to have a 10 nanometer Skyrmion. So now you have two parameters. You have two things in which you can work on. You can have a small kappa, but you can have a large domain wall width, or you can have a small kappa and a small domain wall width. Both might give you the same radius. And you have three quantities to vary, which is the exchange, the anisotropy, or the Jarodzinski-Mori interaction. And that's what we basically did. So we keep the width of the Skyrmion fixed, which is this five lattice constants radius. And then we vary, and this is the this profile was generated by these parameters here. And then we varied these parameters so in such a way that we kept always the Skyrmion fixed in respect of nanometers or lattice constant, but varied the profile. And now you see, if you go to the domain wall regime, that means your basically your domain wall becomes small and your kappa becomes small, the profile looks like this. It is more like a domain wall profile, whereas the opposite, if your kappa becomes large on your Skyrmion radius, so the domain wall width becomes large, you are here in a kind of arrow-like regime. And this has impact, has an influence on the lifetime of the Skyrmion. So here is the renormalized energy profile from the energy of a metastable Skyrmion over to the ferromagnetic state here. And what you see here is the barrier height varies enormously with the Skyrmion profile. So if the domain wall width is small and your kappa is small, then the barrier is high. But if your kappa is large and the Skyrmion, that means the Skyrmion radius is extremely small, and your domain wall is large, then your Skyrmion is not very stable. So that means, I told you before, you need the Dzhalochinsky-Moriya interaction to stabilize this Skyrmion. But if the Dzhalochinsky-Moriya interaction is small, your Skyrmion is small. But if you make now your Dzhalochinsky-Moriya interaction large, your kappa becomes small. And if you make the domain wall small, the barrier is large. So a large DMI is valuable for the barrier. But unfortunately, you are done in the regime where your radius quickly changes or may quickly change with respect to inhomogeneities of the material. So it's a very, very fine-tuning of the material to get the proper Skyrmions, which are stable, have the right size, and move fast. I mentioned to you this equation here is a little bit, yeah, okay, you cannot see very much of this equation. But if you look at the limit of large radii, then you can cancel out a few terms. And then this equation reduces to equation you might have seen before. This is exactly the domain wall equation. And therefore, the domain wall in a certain regime, the domain wall solution is a very good ansatz for the Skyrmion. And you have maybe a few parameters to optimize the domain wall profile, which is maybe this integration condition C or the domain wall with W. And yeah, you know, we are familiar with this domain wall solution. And we have set up a Skyrmion radius calculator for the community, basically. So you can put in your numbers which you like to have and push a button, and then you get the Skyrmion radius. In this talk, I use the shooting method because we want to have a very fast internet web upload. Therefore, we used here the domain wall profile. It has some other advantages, which I may come later to. So far, I focused completely on the micromagnetism. Of course, this is not the full story. We all know we work with metals, B20 materials, thin films, multilayers. Many of us work with metals, and these metals have FERMI surfaces. And these FERMI surfaces giving rise to long-range interactions, long-range exchange interactions, long-range Dzhalochinsky-Moriya interactions. And these long-range interactions are actually sometimes, like here, positive. That means they are ferromagnetic. Here for red, for example, is this iron layer, and blue is this iron layer. And then you see at some distance they are negative. They are antiferromagnetic coupling. And in some regimes, it can happen that this leads to frustration. And this is these competing interactions are not very easy to describe in a micromagnetic theory. So you basically, what you do, you have to go to higher orders. And this brings you to a micromagnetic equation, which is basically more similar or is equivalent to the actual skyrmion mechanism. So usually we call our skyrmion, but our skyrmion is stabilized by a gradient term, by so to say, by a chiral symmetry breaking term, whereas the true skyrmion mechanism was a higher power gradient. And with this frustration, you come closer to these higher power gradients. And we found, this has been worked out by Rybakov and Kiselev, that if you, for example, have certain higher order terms, depending on the material constants A, B, and C, you can have completely different objects, for example, knotted magnetic excitation solitons of different types, if the parameters are right and you have the right materials. I don't go into this today, but it's a different branching direction, because now we go into three-dimensional particles and not into two-dimensional ones. Obviously, what our approach to manage all this, so we have on the one hand the micromagnetic model, in which we often think. Then we have an atomistic spin lattice model, in which we do simulation. And then we have a DFT model, from which we do ab initio calculation from the microscopic theory of the electrons, from which we then basically determine these parameters A and D, which enter, of course also K, which enter into this micromagnetic model, or by other techniques, using other methods, for example, the KKR method, calculating Dij or Jij. So basically, we have this multiscale approach, trying to do this, getting these parameters from the electronic structure, from the electronic properties. Think first what can happen, and then try what the simulation gives you. And I would like to make one important remark here. Of course, micromagnetism has its great values. But I also would like to say it is limited if the skyrmions become small. It has some problems with competing interactions. And you should also realize the important thing. There is a relation between these parameters A on these many long-range interactions J, which is basically a huge contraction. So you have all these microscopic parameters from the nearest neighbor, next nearest neighbor, next nearest neighbor, next nearest neighbor in all possible directions. At the end, you contract everything to an A. And the same happens with the spiralization, where you basically calculate the Jagodzinski-Moriya interaction and contract it to one number for one tensor. That means you can have many different combinations of Jagodzinski-Moriya interactions, atomistic Jagodzinski-Moriya interactions, or atomistic exchange interactions, which always gives you the same micromagnetic parameters. But what happens is, it's not here. What happens is that if you look closely, we showed recently that depending on these microscopic parameters here, although they give you all the same micromagnetic parameters, the lifetime of a skyrmion can be orders of magnitude different. That's an important fact, because when the skyrmion goes over the barrier, you have certain rotations which cannot be caught anymore that correctly by this multiscale modeling, by this spiralization and spin stiffness. And the prefactor of the lifetime as well as the barrier of the lifetime can change by orders of magnitude. And that means you can massage the material. You can change the material, which has nominally the same spin stiffness and spiralization, but can be microscopically quite different and have quite different lifetimes. Okay, when you work with experimentalists and together, the experimentalists have great samples. So they have thallium, platinum, cobalt, ruthenium, platinum, cobalt, ruthenium, platinum, and so on. And you know, if you count up the number of atomic relevant layers, it's easily 40, 50 layers. And this is to calculate these is a little bit too much. And therefore, we have to reduce a little bit the complexity. Instead of these 35 layers here and these 5 layers here, maybe we reduce it to 5. Then there are still 34 layers. 14 of them are magnetic layers. And then you have a small combinatorial problem with respect to the stacking, because experiments have shown there is a big difference whether you have an HTP stacking or an FCC stacking. See, you see here the Skyrmion radius for an ion on iridium with palladium stacked HCP or palladium stacked FCC is quite different. So if you would calculate all possible combinations of HTP and FCC, you have easily a few billion stackings. I'm a great fan of high throughput computing, but this is a little bit too much. So therefore, we have to think about either getting information about experimental input or educated guesses for the stacking order in order to progress here. So any information is extremely welcome. Currently, we operate in a different way. So we say, okay, we calculate simple things. We calculate multi-layers where each layer consists exactly of one layer. So it might be platinum, cobalt, and maybe ruthenium. And then what we do, we calculate these parameters A, D, K, the magnetization, the density functional theory for this cobalt thickness 1. And then we extrapolate by assuming that the electronic structure does not change. This is, of course, an assumption. And basically scale the micromagnetic parameters for larger thicknesses. So we know that the spin-orbit contribution to the magnetic anisotropy and the Jarodzinski-Moriya interaction is certainly an interface-related quantity. Therefore, relative to the number of cobalt layers, you have to divide these quantities per number of cobalt layers if you want to have your energy per cobalt layer. And very differently is the shape anisotropy and, for example, the spin stiffness. These are bulk quantities. So per cobalt layer, they are always the same. And then we can see here how the dimensionless parameter changes now as function of the cobalt thickness. You see the first term related to this spin stiffness makes your kappa larger and brings this Skyrmion radius down. But the shape anisotropy makes the Skyrmion radius quadratic, makes this kappa quadratically smaller and brings you basically to larger Skyrmion radii. So this is a very fine balance where this shape anisotropy varies the kappa and therefore the Skyrmion radius. And the easy axis of these magnets are typically out of plane. And if you increase now the thickness of the cobalt materials, you have this shape anisotropy as function of thickness. And there is one point which is called a reorientation transition. That's the thickness where you change from out of plane to in plane. But prior to this point, there is a point where this becomes so small that you are at kappa equal 1 and basically your radius diverges. So prior you come to this reorientation transition, there is a point where basically your Skyrmion radius explodes. And yeah, and then you can see the Skyrmion radius as function of the number of cobalt layers and things. You can calculate this. This basically we have done now for a number of systems. So we have basically taken cobalt platinum. We have varied the third component basically goes across the 4D series. We have copper, tin, cadmium, things like that, basically across the series. And calculated these parameters. I'm a little bit short in time, therefore I move on a little bit further. The nice thing about these calculations, we get trends because we get trends across the transition metal series. And then you see, for example, the magnetic moment of cobalt changes across the transition metal series. We know which layers are coupling antiferromagnetically or ferromagnetically across the interface. So basically we see here these materials here. This is the ferromagnetic state. This is the antiferromagnetic state. See, the antiferromagnetic state has here a lower energy. So all these gray elements here are basically make the cobalt films couple antiferromagnetically, whereas these pinkish elements are basically coupling ferromagnetically. And with the cobalt moment scales the spin stiffness. The strongest spin stiffness we have for rhodium, isoelectronic to cobalt. And we get also the magnetic anisotropy. You see the magnetic anisotropy of cobalt is largest at the beginning and the end of the transition metal series. The largest one is for palladium. For niobium, molybdenum, technetium, it's in plane. Okay, then technetium is not so relevant. And we can also calculate the Jaroszynski-Moriya interaction. And I would like to point out the following. This black stars here, this is the total contribution to the Jaroszynski-Moriya interaction. It's large at the beginning, it's large at the end, it's small in the center. And here we analyze the contribution to this quantity. You see the most important contribution is the platinum. It's basically the platinum contribution follows the total contribution very well. And now we put everything together. We have the A, the D, the K, and you see each element on this plot. So we have two elements, cadmium and silver. They form one-dimensional spiral states as ground state. At zero field, you cannot form skyrmions. You need a large field to make them, turn them into skyrmions. Whereas for those elements, you get skyrmions at zero field. And you see, for example, the radius can vary in this domain wall radii from 0.5 to basically 0. And if we now look at the domain wall width, which is between 3 and 5 nanometers, you see that we calculate here the profile of the skyrmion. You see, this is this theta pi half line. And then you see the skyrmion radius is in the order of the domain wall. So it's about 2.5, 3 nanometers. And this is consistent with the experiments of Wiesendanger for monolayer type skyrmions, which we have calculated. Now, let me make one or two more comments. One is the finite temperature. So far, everything was T equals 0 calculation. If you look at our spin lattice model, we have a couple of quantities which are two-side quantities, and we have one quantity which is single-side quantity. If you now take the thermal correlations into account, you see that these quantities, roughly, scale proportional to the magnetization as function of temperature to the magnetization at 0 temperature square, whereas this quantity scales with the third power. And now if you put that into our kappa parameters, you see basically this magnetic anisotropy contribution, the spin orbit contribution to the magnetic anisotropy scales differently than the rest. And that means my my kappa parameter is becoming, as function of temperature, smaller. So that means if you look at the kappa values which I have shown you at T equals 0, here is an example for ruthenium and copper. You see ruthenium becomes a little bit larger because kappa becomes smaller, but copper is already on this strong rise. So a small change in this kappa makes a large change in this copper radius. And if you include now also the domain wall, which becomes also larger at smaller, finite temperature, you see that, for example, for copper, the copper cobalt platinum system, the skyrmion radius changes from 2.7 to 5 nanometers. This is basically a little bit more than factor 2 over room temperature. Then I look here at the extrapolated values. So now I'm looking at the Skyrmion radius as function of the cobalt thickness according to this expression which I have shown before. And you see, first of all, that the Skyrmion radius varies even already for the monolayer, depending on the material, by 3 orders of magnitude. But what you observe is if you increase now this cobalt layer, the shape anisotropy becomes larger and larger. And you come to this critical point and you see how the Skyrmion radius changes. That means if you now fabricate your solid and you have an average slightly more cobalt or slightly less cobalt, your Skyrmion radius varies a lot from the point of undetectable by your characterization tool to too large. Okay, I think my time is a little bit up. Let me think how to continue. Maybe it's time to close. And I would like to say that a lot of people have been involved, and I'm thankful to many, many people in this group. And I would like to mention in particular Hongying Jia, Markus Hoffmann, Bernd Zimmermann, Gideon Müller, and Fabian Lux for all the contribution about the Skyrmion radius, about Skyrmion radius solver, about the enormous amount of calculation, the analysis, and so on. And of course, I also thank the funding agencies for support, for example, also DARPA from the United States. And with this, I thank you very much.
Thank you, Stefan, for this very interesting talk. We're ready to take questions. So if you're watching in Zoom, find the participants panel and use the raise hand button under the participants. So first question, Alexei Kovalov, please go ahead.
Hello. So I have a question. So if we have Skyrmion lattice, then smaller DMI will correspond to larger Skyrmion. So it's opposite from what you said. So where does your argument about scaling breaks down?
No, I think it's that there's a big difference. I think if you take, for example, if you take a one-dimensional spin spiral, one-dimensional case, spin spiral ground state induced by the Dzhalachinsky-Moriya interaction, then you know exactly that the pitch is proportional to exchange divided by the Dzhalachinsky-Moriya interaction. So the larger the Dzhalachinsky-Moriya interaction, the smaller the pitch.
Yeah, and that's also works for Skyrmion lattices.
Yeah, but Skyrmion lattice is the same.
Yeah, so it's opposite from what you said. So I just wonder, where does your scaling argument break down?
Now, I think you have to see for different scenarios. So I studied the metastable case. But if you go to the Skyrmion lattice, you study, so to say, the ground state. Then it's the opposite.
It is you also minimize energy, right? When you find ground state, it's the same procedure.
Yeah, no. You study a periodic structure. Whereas here you study a single object immersed into a single metastable object immersed into a ferromagnetic state. So that means basically this ferromagnetic state wants to squeeze you and makes the Skyrmion very small. In the Skyrmion lattice state, you're in a periodic state, and then the argument are exactly the opposite. It is exactly like yeah, it's exactly the opposite. That is confusing, I know. Therefore, I know, I see this sometimes in papers, and therefore I pointed this out here. Exactly, I wanted to point this out in this talk. That's exactly opposite. I wanted to first present actually the Skyrmion lattice, but I thought it's too much. But that's very funny. And you see that the spin spiral ground state is the pitch is A over D, and exactly the larger the D, the smaller the pitch. But for the Skyrmion lattice, it is the same, but for the single Skyrmion, it's the opposite.
All right.
It is kind, you know, when you study one-dimensional systems, there is, and you study everything as function of this micromagnetic parameters, you have a phase transition at kappa equal 1. And this kappa equal 1 is exactly the phase transition from the spin spiral ground state to the ferromagnetic state, on which you on top can have a domain wall, which is metastable.
All right. So I guess this periodic boundary conditions needs to be taken into account with care. Yep. Thank you.
Thank you. Further questions, please. Please use the raise hand in Zoom.
But I must say, it is very confusing. I struggled also with this.
If you're watching on Twitch, you can type your question in the chat box. We'll take that too. Sucheta, please go ahead with your question.
Hello, Professor Blügel. This was very enlightening talk. So my first question is to you. Being an expert in this field, how do you foresee the future of individual skyrmion to be used in a real-world application? Or keep it, I mean to say that which possible prototype or device can be readily proposed using the potential of individual skyrmion in near future you can predict?
You know, I'm a theoretical physicist and I'm extremely bad in technology. So I always listen to my colleagues when they say something about technology. But if you ask me my personal opinion, which you should not take too serious, is I think the Skyrmion motion at low energy and reliably without pinning is not so easy. So I think probably maybe it has a great future in neuromorphic computing in this direction rather than maybe in racetrack. But maybe I'm wrong. Maybe also racetrack will have a future in the sense that people overcome the pinning problems and these kind of things. But we should also think keep our eyes open for neuromorphic computing. Yeah.
I see. Okay.
Kind of
and I have one follow-up question, which I think you will be like the best person to ask, because you have like you are very familiar with all the energy minimization and energy associated with stabilization of skyrmion at room temperature. So suppose an experimentalist or a growth person wants to reliably stabilize a skyrmion in some system. Then according to you, which will be the preferential system to start with? I mean, either this could be a multi-layer with PMA or DMI, or it will be a pattern structure, or maybe a ferrimagnet. So what is your standpoint here?
You obviously realized in my talk that I stressed very much the importance of the magnetic anisotropy. It's a very small but delicate quantity. And that means also the DMAG, or the way we say DMAG, means the dipole-dipole interaction plays an important role.
Mm-hmm.
And that means by varying or changing the dipole-dipole interaction, you can also move the size of the skyrmions and the stability of the skyrmions. And it means, for example, some people work with cobalt gadolinium or iron gadolinium, where you work close to the compensation point. Then, of course, your magnetic moments are on average 0, and maybe the magnetization is very small. So I would think most important is that you get your material under control, that you can be in a regime where, first of all, you have skyrmions which you can detect. It might be that you have wonderful small skyrmions, but if they are below maybe 20 nanometers, 25 nanometers, maybe you have no tool at hand to see them. I believe that many people have wonderful small skyrmions, but maybe the right skyrmions, but if you cannot detect them, it might be not the best one for you. So maybe good skyrmions might be skyrmions which you can easily detect, maybe 50 nanometers, 60 nanometers, 70 nanometers skyrmions, and then using multilayers. I think antiferromagnetic multilayers or ferromagnetic multilayers is totally fine.
I see. So in antiferromagnetic system, I think the minimization of Skyrmion Hall angle or the Skyrmion Hall effect is also another plus point. Do you think so?
Yeah, that's true. Yeah.
Okay.
Yeah.
Thank you. Thank you so much.
Janko, please go ahead with your question.
Hi, Professor Blügel. Great talk. I have this question, touches on the spin reorientation transition. Just like you mentioned, responding to the previous question, magnetic anisotropy is a very subtle thing, and you know this better than most of us. So when you, for instance, showed that plot where depending on the thickness of the cobalt layer, things go down, and then there is a spin reorientation. Typically, since the Dirac factor hardly depends on these small thicknesses, it will be almost one in one direction, zero in the other. So traditionally, one speaks of surface magnetic anisotropy. Is it so that somehow it was included in your considerations, but you never mentioned it? Because that's usually what people think about when there is thickness dependence of that kind.
Yeah, maybe I didn't express myself clearly enough. That's what I actually meant. It's basically, of course, you have a bulk contribution to the magnetic anisotropy, and you have surface or interface contribution to the magnetic anisotropy. But the interface contribution is by far the largest. And that's basically the one which I took into account, and that is basically the one which basically drives the system perpendicular.
Okay, yeah, right. Okay, thank you.
I will go for 1 second, go up because I switch on some light. It's getting dark now.
Okay. Any further questions? Please use raise hand if you'd like to ask something. So Stefan, I have a question. So in the regime where the Skyrmion radius goes to 0, this can't be the right answer because there's a finite lattice parameter, right? So what is there anything special that happens in that case? So is there some generic answer?
Very sorry about this. I should have said this. Of course, it doesn't make sense to say I have my Skyrmion radius is 0.04 nanometers. I mean, the micromagnetic theory is, of course, a theory which breaks down at a certain length scale. And of course, if your Skyrmion becomes smaller than a few times the lattice constant, then of course the Skyrmion feels the coarse graininess of the underlying lattice. And basically this idea that the Skyrmion is a smooth object, this idea breaks down. And then in some sense, if the Skyrmion becomes too small, you can either say the lifetime becomes very short, or you can say the topological protection breaks down. Yeah. So in principle, I would say, of course, what I showed is basically the scaling behavior. But it is true that I should have made a cutoff at maybe, I don't know, few lattice constant.
Mm-hmm. Okay. All right.
Thank you for pointing this out.
Yeah, I was just wondering if the role of the DMI somehow changes in that limit, or is it qualitatively the same as in the continuum limit?
Basically, the continuum limit is, of course, a contraction of, so to say, of the DMI over many sites.
Yeah.
So to say. But of course, if your skyrmion becomes too small, it does not make sense anymore to work in that limit. Then you better work directly with the spin lattice model.
Yeah.
And then you see directly that, of course, you have sometimes three-dimensional vectors, Geodesic vectors pointing in different directions. Then things become certainly more complicated.
Okay, so there is no general result that, let's say, stronger DMI corresponds to smaller radius or larger radius in that limit.
That's a good question. Yeah. I think there is a big difference whether it is whether your skyrmion lattice, you study a skyrmion lattice or a single skyrmion. I think in the skyrmion lattice, maybe, yeah, a strong DMI, of course, helps you. But if you study the single skyrmion, I do not know how the scaling relation is on the atomistic scale. I didn't check this.
So I'm also a bit struggling to understand the difference between the lattice and an isolated skyrmion. So I understand the scaling that, the density of the DMI goes as 1 over r, and then the Jacobian goes as r, the area goes as r squared. So your DMI prefers larger radius. In the lattice, it's cut off by the Skyrmion lattice constant. So is it a good way to think about it qualitatively, or is it something else?
That's a good point. I never thought it looked in this way. I'm more, yeah. Have to think about this.
Okay.
Yeah.
All right. Thank you, Stefan, very much for this talk. So you can thank the speaker by using the reaction button. There's a clap and there's a thumbs up